video, I will be showing you how you can find the best solution for an optimal transportation problem using the UV method. Previously, I did a video on how you can find the solution by looking at the table and slowly adjusting where you find needs to be adjusted. This time, using the UV method, we will have a surefire way of finding it, and it is also the way that computers, like Python, find the solution. Let's first have a look at our scenario. Let's imagine that you own a car manufacturing company. You have 3 warehouses and 4 factories across the country. Each of the factories lacks an amount of car parts, and you have them in your warehouses. In warehouse 1, you have 200 truckloads of car parts. In warehouse 2, you have 300 truckloads. And in warehouse 3, you have 500 truckloads. Here you have the amount of truckloads that each factory requires. Here you have the cost in thousands of dollars it costs for transferring 1 truckload of car parts from warehouse 1 to store 1. Here you have the costs in thousands for the rest of them. You want to find how can you find the minimal cost for transferring all the car parts to all the factories? So, how much from each warehouse should you transfer to each factory? First, let's have a look at the formula for finding the total cost of transferring all of the car parts to all of the factories. Here, I'll substitute these variables in. Here will be the cost per truckload to transfer, and here will be the amount of truckloads we choose to transfer to each factory from each warehouse. The total cost equals the cost here times the amount we transfer plus the amount it costs to transfer a truckload from warehouse 1 to store 2 and the amount, and here we plus all of these. When you have a look at this, you can see that it's a linear equation. A linear equation is when all of these variables are to the first power. Now, what good is that? When we have a linear equation, let me first go back to that picture. You can see that this linear equation has its restrictions. So you see that the restrictions are, let me go back to this. Here, the maximum amount warehouse 1 supplies is 200. So, over here in our formula, let's see, x11 plus x12 plus x13 plus x14 must equal to W1. And same goes for the rest of these. x21 plus x22 plus x23 plus x24 must equal to W4. And in these columns, x11 plus x21 plus x31 must equal to S1. So if we want to remove something from here, we'll have to add it. We'll have to add that same amount somewhere over here. And we will also have to add that same we'll also have to add that same amount somewhere here. After we add that amount, for example, we add it here, we will have to subtract that somewhere here. Now the restrictions will be a polygon and the corners of the polygon will be the lowest corner will be the minimum, and the highest corner will be the maximum, and such. If we have a nonlinear equation, we will get continuous lines, and we won't be able to find any corners. So it will be difficult. It will be difficult to find the minimum simply by adjusting our x and y, our x. With that, we can first find an initial corner, and then we can slowly adjust until we get the minimal corner. Over here, to find my first corner, I want to meet this restriction here where this plus this plus this must equal to this. So, from warehouse 1, I transport all I can to factory 1. Then what's left will be transported to the consecutive factory. Here, this will be empty now. We move on to warehouse 2. We transfer all we can to the remaining store here, factory. Then, as you can see, we transferred all our car parts to all our factories. Now we have our initial corner. It's time to adjust. But before we do that, let's first see what's the value of our corner. So this times this, we get 3,150. So if we use this one here, we will spend a total of $3,150,000. First, we have to check whether or not we can adjust to get a smaller value. So let's see. Now I'll set my U variables, which are the rows, and the V variables, the columns. To set them, let me see here. First, I'll change all these to variables. We want to set it so that U1 plus V1 equals to C11. So here's the cost per truckload transported from warehouse 1 to factory 1. We set U1 equals to 0. Since that is the simplest form, we want it so that this plus this equals to this, and this plus this must equal to this, and so on. So we get C11 must equal to U1 plus V1, and with that we can find V1 equals to C11, since U1 is 0. Now in this pattern, we go from here and then we zigzag all the way down. We find V2. Here we get V2 equals C12. Now we go down to find U2. We know that this plus this must equal to this. Here we get U2 equals C22 minus V2. And we already get that V2 equals to C12. So it's C22 minus C12. Here I find the value of V3. Then I find the value of U3. Then I find the value of V4. The way we test whether or not we should change the value of x in either of these squares, it's Tij, I is the row, j is the column, equals to the u of that row plus the v of that column minus that cost of that square. If there's any Tij that is greater than 0, we should continue to adjust. So, for example, if T21 is greater than 0, we should adjust X21. And when all of Tij's are smaller or equal to 0, our adjusting is complete, and we can find and that will be our minimal corner. Why is it that if Tij is greater than 0, we should adjust Xij? So to explain, I will take a random square, for example, row 2 and column 1, why is it that if t21 is greater than 0, we should adjust x to 1? Here we have our formula for testing it, and when you look at this, we already got that u2 equals c22 minus c12. So it's actually this plus, we have v1 equals to c11. Now this equals to this. And as we previously saw, let's see. Wait, first they say if c22 plus c11 minus c12 plus c21, if that is greater than 0, we should adjust. Well, first, we should remember that we are only adjusting the ones where our x is 0, so we have no workload. So when we say we have to adjust, we can only plus x. And when we plus x here, we should minus x here, and plus x here, and minus x here. When we minus x here, we will remove c11 times x amount. Here we will remove c11 times x. So we will remove a total of c11 plus c22 amount of cost. Here we'll add on c12 and c2 plus c21. So if we remove more than we put back on, that means that if we adjust, we can save something. So we already found our initial point. Time to adjust. See if we need to adjust. Let's see if we need to adjust t13. We have this formula, and here we have the values of the u's and v's. This equals to -5, and that is smaller than 0. And here we test t14, then we test t21. Here we get 5, which is greater than 0. Before we adjust it, we will test these. We test more, even though we already found one, is to see if we can find one that is greater than this here. If we get one of the t that is greater than t21, we should adjust that one first. So we want to adjust the one that we can save the most. So over here, so first we test this t11, but actually we don't need to test t11 because we already set it will equal to 0, because t11 equals to u1 plus v1 minus c11, and we already set c1 equals to u1 plus v1, so of course this is 0. Same goes for t12 and all these in this pattern. Now, what we need to test is t13. We get it equals to 0. t14, and we test, let's see, t24, t31, and t32. We don't need to test t21 anymore because we already have, and it's already adjusted. And we get all these values are smaller or equal to 0. So that means we are finished. We can find our minimal point. So the minimum point is, we put it into this formula, we get 2,650,000. So these are actually in thousands. We get 2,650. So the total amount of money that we save will be this minus this times 1,000, which is, we will save $5,000 from our first corner to our result corner. Now let's have a look at our Python program. Here, let me run this. We get the same result, 2,650.